This question number 3 on the circuits review packet. You've got a motor, and it says you're asked to design a circuit to supply an electric motor with a 1 milliamp of current at a 3-volt potential difference. And the first one says determine the power to be supplied by to the motor. We know that power is equal to voltage times current, and we know the voltage supplied to the motor and the current delivered to it. So this is pretty straightforward. We're going to get 3 volts times 1 milliamp, or 0.001 amps. When you run that, you get 0.003 watts, or we can call that 3 milliwatts. Would be an acceptable answer. That's question A. Part B says determine the electrical energy. Power, by definition, is work over time, and work is the same as energy. Those are equivalent via the work-energy theorem. So therefore, energy is going to be equal to power times time. And so now we're going to get that 3 milliwatts, or the 0.003 watts that we just solved for in part A. We're going to multiply that by 60 seconds. And when we do that, we're going to get 0.18 joules. 0.18 joules being our answer for the amount of energy supplied to the motor in 60 seconds. Okay, moving on to part C. Question C says, okay, operating as designed above, the motor can lift 0.12 kilogram mass a distance of 1 meter in 60 seconds at a constant velocity. So they ask you to figure out then the efficiency of the motor. Cool question. It involves looking at mechanical power versus electrical power. You could understand efficiency by simply saying that it's the mechanical output, or the output power, divided by the input power. And in this question, the input power is the electrical power. So I'll say the electrical power that I just found, we just solved that in part B, that's or part A, that's the 3 milliwatts. And we need to figure out then the mechanical power, which is really what you're getting out of the system. By definition, that's what efficiency is. So the mechanical work that's done is equal to force times distance. So and the minimum lifting force, if I'm moving it at a constant velocity, is simply going to be the weight of the 0.012 kilograms. So force times distance, I could say, is going to be mg. That's this upward force times the distance. If I were to sketch a quick free body diagram over here, whatever lifting force I need to apply with needs to be equal to the weight in order to move it at a constant velocity. Okay, so mgd, sounds like a beer commercial, but anyway, 0.012 kilograms times the acceleration due to gravity, 9.8 meters per second squared, times this distance of 1 meter. And so we get a total work done of 0.1176 joules. So that's how much work I did. And now I can figure out how much mechanical power that is by simply dividing that number divided by the 60 seconds. And so therefore the mechanical power, P sub m, is equal to the mechanical work divided by the time. And so the mechanical power is the 0.1176 joules over 60 seconds. And I get now 1.96 milliwatts. So we can see that for dumping in 3 milliwatts, I only get 1.96 milliwatts of usable power. Okay, so my efficiency is going to be the 1.96 milliwatts over the 3 milliwatts that we previously found, and we see that this is unitless, right? So we end up getting a percentage. If we multiply that by 100, we'll get 65.3% is our efficiency. So that's our answer for part C. The last question, part D, they want us to, in the space below, complete a schematic diagram of a circuit that shows how one or more of these resistors can be connected to the battery and motor so that 1 milliamp of current and 3 volts of potential difference are supplied to the motor. Be sure to label each resistor with the correct value of its resistance. So we need to basically drop voltage from the 9-volt battery that's been supplied. So that's what we get to use. And we need 3 volts of potential difference. So I want to figure out how much resistance the circuit needs to have in order to drop 6 volts. So basically, what I'm doing is I'm looking at V equals IR. This is basically what I'm rearranging, solving for R, where V is 6 volts and I is the 1 milliamp that ultimately needs to be supplied to the motor. So I'm going to get 6 volts over 1 milliamp, or 0.001 amps. And when I do that, I get 6,000 ohms. So in other words, the circuit elements need to have a resistance of 6,000 ohms if they're going to drop 6 volts. So a couple of different ways to sketch it, but here I'll draw this sideways. Here's my 9-volt battery, positive terminal, negative terminal. I need to come out and have a total of 6,000 ohms of resistance, so I can do it with a 1,000 ohm resistor, which I'm given, and a, not a 6, 5,000 ohm resistor. Here's my motor. So my sketch looks like that.